In this tutorial video, I will demonstrate how you can solve a stack cookie 4, and let's take a look at the stack cookie 4.c. And here is a main function, and then it has a non-main function on it. And then inside the non-main function, it will call input function, and then this is our vulnerable function. And then what it does is it has a buffer with the buff size, and then it will read up to buff size multiplied by 2. So it will store into the global buffer, which has like the buff size multiplied by 2 as a size. So it does not have a buffer overflow, but it will copy byte by byte from the global buffer to the buffer I from 0 to the length. So there will be a possible buffer overflow here if the size of the size that we send. So the return of the read function will be the length of the bytes that the program has read, and if that is more than the buff size bytes, then we can launch the buffer overflow attack here. And it looked like very easy, but why? This is the stack cookie challenge 4. The reason is if we check like the status of this program, it says a stack canary has found. The reason is, let's get into the stack cookie and disassemble the input function. And what it does is, so at the start of the function, it will move ZS0x14, which is the storage for the stack cookie, to EAX, and then put that to EBP-C and clear the cookie value. So the stack cookie value is stored in the EBP-C, and then when it returns, so it will fetch EBP-C, place the cookie value to ECX, and then apply XOR with the value in the GS0x14 to ECX. So XOR, if two values are equal, it will return it will store the value 0. And then JE jump equal is equal to jump if 0. So if two values are equal, then it will jump to 169, so leave and return. But if two values are mismatching, then it will call stack check fail. So this is a GCC Propolis, the GCC's default stack cookie. And then if we cannot pass this stack cookie check, then we will meet stack check fail. And unlike stack cookie 3, it does not have fork system call at all. So you need to run the program again and again. If you crash it, then if you rerun the program, then this cookie value will definitely be changing. Then how can we exploit this program? And to do that, we need to analyze the assembly a little bit, and then let's do that. So I will just copy all the assembly lines, and then I will create the disassemble text file. And then this is our disassemble text file. And then we know that the stack cookie is at EBP-C, right? And then it will call puts and read, and from the read function, it will read to the global buffer gbuff, right? Yeah, and then up to size 256 0x100. And then there will be a for loop. So maybe for loop started here. So it will jump to 113, and then there is a jump back to 84. So we can estimate our for loops will be around here. Yeah. And then from the printf call, because so the source code of the printf, so the the second argument of the printf is the buff, and this is the first argument, and this is the second argument. So second argument comes from the address of the EBP minus the 90. So now we can get the where the buffer is. So our buffer is at EBP minus 90, right? So now we know that, and then this might be int. So we are analyzing this for loop. Maybe I can move the code a little bit up to match side by side, and then from here we can write it as int equals 0, and then jumps to 113, and then 113 is here, yeah. And then this might be incrementing statement. So EBP minus 10 is I. This may be I plus 1, and then store that back to I. So this is this one, and then this is the comparison instruction, and then it will compare. This is I, and then EBP minus 94, and then where EBP minus 94 comes from is the EAX of this one, and then that's the return value of the read. So it's exactly this one, so we can interpret this as EBP minus 94 stores the length variable, the text length that we send to the program. So return value of the read. So, and then now we know that this is length, and then if this value is less than length, then it will go back and run again and again. So we can write the for loop as for I 0 I less than length I plus plus. Then do this. And then the code for this is a buff I is a g buff I from here, and then so EAX will store I, EDX will store I. And then this instruction is actually 0x804860 EDX. Then store that to EDX. And then we know that EDX is I. So maybe this will be EDX is G buff I. And then now this instruction is so EBP minus 0x90, and then EAX multiplied by 1. And then multiplied by 1 can be ignored, and then we know that EAX is I, and DL. And the value DL comes from the EDX, the last byte, so it'll just copy 1 byte. G buff I. Yeah. So this is how we interpret the code, and let's think about some of the structure of the variables. So I will just copy here to there. Then I will make this as some of the comments. I will use this code snippet to forge the buffer that we would like to use. Then to write an exploit script, so we will do some of the common thing. And then we will run process stack cookie 4. Then we will construct a buffer here and then we will send the buffer, and then the interactive, and then I can also maybe copy the shellcode from this code. So I got a shellcode and then set it as an environment variable and put the environmental variable, the shellcode, to the process. Then now I have an address of the shellcode address as FFFFD100. It worked, right? Yeah. So this is the default setup. And the important thing is that we have a stack cookie at the EBP minus C. Yeah. And then let's draw about the buffer. So we have a buffer. And then what will be the length of the buffer? And we have a buffer at the EBP minus 90. And then we have the variable I at the EBP minus 10. So we can think it as like the buffer size as a 0x80. And then we have variable I, local variable I here. So this is at EBP minus 0x90. And then at the EBP minus 0x10, then we have a variable I. So minus 10 minus 90, so we have a length 80. And then at the EBP minus 0c, what do we have? We have stack cookie at here, and then some more bytes, and then minus c, minus 8, minus 4, minus 0, so we have a saved EBP, and then return address. And currently the problem is not that we don't know the stack cookie value, but the interesting thing is that we have a loop for int I length plus I, and then we have a loop of this one. And then think about if what will happen if I equal 0x81. That is, so it will fill the last byte of the buffer at 0x80, and then with the index 0x81, then it will overwrite the last byte of the variable I, so that we can change the value of the variable I. That means, what if we change the variable I to point return address directly by skipping all these bytes? So what we will do is, so at the time of the, if I is 0x81, then it will have 81 000000 as 4 bytes. But if we copy 1 byte as a, so let's calculate some of the distance. So this is a EBP minus, so this is index 80, and then 84, 88, 8C, 90, 94. So if we change this value to 93000000, the reason why 93 is that we will update the value as 93, and then it will have an increment, so it will point to 94. Then we can skip the entire this part and then directly overwrite the return address. Let's do that. So we can fill the buffer as 0x80 bytes, and then we will fill the variable I, so it will store 0x81, but we will change that to 0x93. So P8, because it's a 1 byte, 0x93, and then we need to fill all these bytes because it will copy from our data, which is in the global buffer, to the buffer. So we will fill 0x94 minus 0x80 minus 1 because we put 1 byte here. So we put the character B this amount, then we can fill up to this point. And then we will put the return address P32 shellcode address we put on the stack's environmental variable. Yeah. And then I'm not sure it will work or not, but let's check how it is being executed in GDB. To check that, we'll change the code a little bit. So set this and then GDB attach P, then we will see the result. And before doing that, I will copy stack cookie 4 as a stack cookie X, and then run the script. So now we are in the GDB. So I will disassemble the input function and then take a look at the, I will break at this instruction where we overwrite the target variable. So before overwriting the variable, I will set the breakpoint, then continue. So right now the index is stored at the EDX. So EDX is 0, index is 0, 1, 2, 3, 4, 5, 6, 7, 8, and then it will just copy all the A's to our stack. So if we do EBP minus 0x90 is the buffer, and then we will see A, and then go one more instruction, then the continue, then another A here, then continue, another A here, and then it will fill A, and so on. And then let's continue up to EDX value goes A0, because that's where we are interested in. 60, 70, this is 7F, and then this is for 80. Yeah. So when our index is 80, then we can check what's the value in the EBP minus 10. So it points to the 80. But the value we will store at here will be exactly at the EBP minus 80. So next instruction, we fetch the value 93 to the EDX, and then we will put 93 to the local variable I. So right now the local variable I is 80, but after running this instruction, the local variable value has been changed to 93. Yeah, and then so EAX is 93, and then add 1, so the index will be 94, and then that will be stored as the local variable, and then because this is less than the length of the what is in that variable? So less than the length of the entire buffer, 99. Yeah, so we can continue. And then next, so E plus 4. This is the return address, and then our return address is this one. But after running these two instructions, it overwrote the last byte, and then after running this two instruction again, it overwrote second bytes, then it overwrote the third byte of the return address. So EBP plus 4 is always the return address. Then, so it successfully overwrote all the return address. And then it will exit the loop, print out our message, and then it will check the stack cookie value, then jump equal, so we didn't change any value on the stack cookie, so the value is equal, so it will move to reave and return, and then finally returns to the shellcode. So the interesting thing here is that by changing the variable, the last byte, we can change the index of this for loop to skip the stack cookie part and then directly overwrite the return address. So the stack cookie is a good defense against the sequential overwriting of the buffer overflow, but if you can control the variable or how your buffer overflow overwrite the memory for the what kind of location of the stack, then if you can skip the stack cookie part and then directly overwrite the return address or save the EAP, then you can still launch the attack. So to finalize the attack, just remove gdb.attach and change this as a stack cookie 4. Then if I run it, then I can get the shell.